This is the microphone I'm speaking into at this very moment. It was a cheap microphone I bought from some Chinese reseller on eBay. The problem I have with it is that its levels are too low to trigger a hardware condenser that I've bought, which I thought might enrich my recording setup a bit. Now, you can buy devices which go in line with the microphone and actually amplify the signals without providing distortion. One such device is the FETHead Phantom. Now, just a warning to all those out there who might consider buying one of these, the FETHead does not pass phantom power, the FETHead Phantom does. So that means if you have a microphone which does not require power, you need the FETHead. If you have a microphone that does require power, you need the FETHead Phantom. Surprisingly enough, I couldn't find many people actually analyzing this device and from an electrical perspective. I did find this video by Cameron Gray, which I will link in the description. While he does take it apart and get some nice footage of the PCB, he doesn't really have an electrical background and he couldn't really tell us too much about the device. So I decided to take my own apart. You need to remove this screw on the bottom, and then the entire board will slide out. It helps to pull on the pins with pliers, but try not to damage them. Now, you'll notice here that there are 3 soldered wires. These are actually going to the 3 pins. You will not be able to slide this device all the way out without desoldering these wires. And because I didn't want to do that, I just slid it out to here and did my analysis. You can see here that there are 4 devices in pairs that are just connected in parallel. It helps to get the light at a sharp angle, and you can really see the traces picked out. You can also see that there is a resistor and some traces hiding under here. So you'll need to take multiple photos at different angles to really capture all the detail. What you can do then is go into an image editor, crop out the rubbish, and just try and square up the board as best you can. You then need a photo of the backside. This is one I took from Cameron's video. Now you can see the traces on here and you can see the components. So what you can do is start drawing connections. You can see that's the hidden one there. Once you have a reasonable idea, you can start using a multimeter to just verify. So for example, this device here has a wire on one side and it's connected to this pad down here. I can just about use my multimeter to connect to those and just beep that out with continuity to verify that connection. It helps to put a white background on here, and then you can redraw what you see in a slightly clearer way because it's all sort of jumbled together. This is my first pass at doing this. You will never get this right the first time, so I would advise doing this and redoing it. You can see these 2 JFETs are just connected in parallel. So in the future drawings, I simplified that to just drawing 1. Eventually you can get something like this, which is semi-decent. This is the device. It's a K209 silicon JFET. So JFET is this junction type. You can see its parameters here. I would highlight this forward transfer admittance, which I would always call transconductance. You can see that varies from 4 to 15 millisiemens, and it doesn't give a maximum, which is a bit worrying. So who knows really what the variation of these things is off the production line. Now, I didn't actually try to measure the bias voltages. What you'd have to do is solder a piece of wire on the board and just probe that while it's in operation. You can see the parameters here. I want to highlight a comment on Cameron's video by Sienna Gears. Sienna was concerned that they're connecting two devices directly in parallel, and I feel the same way. The classical kind of wisdom from your undergraduate circuit theory lecturer will be that you can't rely on devices to be the same. Now, this was extremely important in the days of BJTs. The gain of your BJT might vary from 50 to 200 from the same devices on the same production line. So that is going to be a real problem if you're assuming that they're identical. The other interesting bit of information is that this is kind of a second generation device. It used to use a pair of K170 JFETs, which are no longer available. It's very interesting to note, so even though they look the same on the outside, if you have an older JFET, it might actually be very different. So this is the circuit that we're left with. This 2M and 2F and 3M and 3F refer to the XLR connector. Pin 1 just goes to ground, and that's also connected to the case, so I didn't bother to draw it. You'll notice that the only asymmetry is this 22 microfarad capacitor. I'll talk more about this later, but I suspect this may be problematic. Using symmetry, we can simplify this circuit further. I drew this capacitor in, but nonetheless, we know that there's only one on one side. You can see that we have a 10 microfarad capacitor down here. Now, what this will do is block DC current, so if we put a voltage through this 2M pin, or even the 2F pin, it will be able to exist on this node and bias the device. However, any AC signals will be conducted away, so you can treat this as a ground through this resistor. And that's what I did here. This is a small signal circuit equivalent. This resistor and inductor are essentially a filtering mechanism, and that will take care of any high frequency oscillation or ringing that might exist in the circuit. Just looking at this circuit, you can see that the output of the device goes back and is connected to the input, so there is a good reason to put some inductance there. Now, I'm not going to dwell on this too much if you're not familiar with electronics. Just note that this question mark is because it's connected to a cable, and it's not necessarily clear how that would look electrically, but we can just imagine it's some very high impedance, essentially open circuit. And I drew this output node here, but in reality it goes back through the cable. So the device is loaded with this 1.5 kilo ohms, and ignoring these other nodes, as I said, you can see that this ID current is flowing through this resistor, but the direction is wrong for the resistor because it goes into the device. So this voltage will actually be minus ID times RL. And looking at this ID signal, you can see it goes through the device and down. Now, you might think that there's this third connection where it could go, but the nature of a JFET is that it's a reverse bias diode, so there will not be any current flowing through the gate pin. The ID is going to flow down and through this RS resistor, and looking at this direction, you can see it's going into the resistor, so this doesn't need a minus sign. Now we want to know the voltage at this input node, so that we can call this VG and this output VD. So if we do the current ID times RS, that's the voltage at this source pin. Then if we add the voltage VGS that gets us to this one here. We can use this to work out the gain. This is a very standard analysis. So as I said, we need this minus symbol here, technically, and you end up with this equation. If you don't know anything about transistors, this might be a little confusing, but the idea of the transistor is the gate controls the drain. And the way this works in practice is you have a voltage between the gate and the source, and that determines the ID through some constant of proportionality. So that just means if you put 3 units in, you get maybe you would get 9 units out, or if you put 1 unit in, maybe you would get 3 units out if that constant was 3. So what does that mean? We call this the transconductance normally, which is given the symbol GM, and we can use this in our equations to work out this value. So this GM VGS replaces the ID, and you can use that to simplify this equation and get this 4.5 volts per volt, or should be minus. Now, don't worry too much about this minus sign. If you think about AC signals going to a speaker, it really doesn't matter if they're inverted necessarily. It just means that the phase of the signal is flipped by 180 degrees. So in dB form, we can take the 20 log 10 because it's a voltage, and that gets us to 13.6 dB. Now, as I said in this note, the datasheet GM was 15 millisiemens, but actually there's 2 devices in parallel, and the GM is, because it's an admittance value, it will add in parallel. Now, additionally, we were just analyzing half of that circuit, so in reality we have to double this, and we get this value 19.08, which is very close to the 18 dB gain advertised on the box. That's what the circuit analysis is telling us. Now let's go over to the bench and actually take some measurements. This is a Behringer Euphoria UMC22 2-channel audio interface, which is going into my laptop that's running Tenacity. The channel 1 and master level knobs are set at the 9 o'clock position. I have my inexpensive Toner branded microphone pointed at my phone, which is going to play a YouTube video of a sine sweep. This is a Tritron inline amplifier. This one is called the FETHead Phantom, which means that it passes phantom power, which is required for my condenser microphone, otherwise it will be unpowered. This is the microphone with the XLR cable going straight into the Euphoria interface. Using Audacity or any of its forks, you can plot the spectrum using the fast Fourier transform. That will give you the amount of signal you're getting, the amount of power at a given frequency. So that's why we have frequency on on the x-axis there. I've also plotted it in a logarithmic scale, which is why it goes 100, 400, 1600, etc. Now, because we're using dB units, the gain is actually just the difference between them. So I subtracted these in Excel, and you can see the gain result on this graph. In the regions over here where you see this kind of wiggling, I think that's a problem with the measurements I was doing. I'm not entirely sure why, but this is also very low power. You can see particularly this section here is around minus 90 dB, which is extremely low. So I wouldn't take that as anything. You can imagine that if I took lots of data and averaged this signal, that it would be a much smoother roll off, something like that. Extrapolating from this small section, you can see that the gain is pretty linear, and it's around 15.5 dB, which is a bit short of the 18 dB that we were promised on the label. I hope you found that interesting. We took a look at the FEThead, looked inside it, checked the component values, worked out the circuitry, and we have a pretty good idea of how it should work, and we know what the expected outputs are. However, we didn't get that when we actually measured the gain. The next step, I think, should be to investigate the power supply. So if our device isn't getting the drain voltage from the phantom power supply, then maybe it's not going to give us the gain we expect. But we'll have to save that for the next video.